you hear me? Can you hear me, Ivan?
Yes, perfectly.
Thank you. So, due to the tough schedule, I think we have no option to wait. We have to start now. And for this session, the first speaker is Professor Rustem Kalmetev, right? From Keldysh Institute of Applied Mathematics.
Yes, hello, dear colleagues. Can you hear me?
Yes.
Okay, let's try to start translation.
Okay, 25 minutes.
Please make it full screen.
Just a second, please.
Ctrl-L.
Can you see it now?
The same. Yes, very good.
Okay, thank you. First of all, thanks for introduction and thanks for great opportunity to give this talk. The title of my talk is Quantum Decoherence via Chernoff Averages. And actually, the talk will be about some approaches for effectively numerical modeling of non-unitary evolution of quantum systems by averaging the unitary ones. And this talk is based on our joint work with Professor Yuriy Nikolaevich Orlov and Professor Всеволод Janovich Sakbayev. The results of this talk can be found in these two papers. First one is devoted to the study of convergence of Chernoff iterations for a certain class of operators. And the second one is about application of this technique to the quantum systems modeling. The general setting is the next. We consider the Schrödinger equation and its solutions given by the time evolution operator S, and consider the sequence of Feynman-Chernoff iterations consisting of random operator value functions of compositions Si with argument T over n. And we suppose that Si is a sequence of independent and identically distributed random variables. Actually, this is a random operators, and by random operators here we mean mapping from some sample space omega to the space of bounded linear operators, which is measurable with respect to some standard base of weak operator topology. And we define the expectation of a random operator such that this expectations doesn't always exist, but in our cases, which we will consider, these expectations does exist. Okay, let CS be a topological space of strongly continuous operator valued functions, and the topology is generated by the family of these semi-norms. So, under certain conditions given by Chernoff theorem, the sequence of Chernoff averages will converge to some semigroup that can be considered as a semigroup describing time evolution of some open quantum system. And according this convergence, we can consider operator on the left-hand side as an approximation, numerical approximation of the semigroup on the right-hand side. The simple example is solutions of stochastic Schrödinger equations governed by the Wiener process. In this case, the time evolution of average density operator is governed by a Lindblad equation or GKSL equation. And on the other hand, we can approximate the solution for density operator as a Chernoff average of this form, where we used the standard approximations of Wiener process. So the Xi, IID, random variables with standard normal distributions. Actually, in Formula 11, we have compositions of exponentials of unbounded operators. So in general, we can't compute these exponents directly. But if we consider some special forms of Hamiltonians, then we can do it and use this formula for effective approximation. For example, we can consider Hamiltonian of this form. This is a general form of Hamiltonian that preserves coherence. That is the states that are initial coherent remain coherent during the time evolution. And in this case, we can analytically write the solution analytically by some affine transformation depending on time, acting in the complex plane of coherent states. And if we have initial state not as a coherent state, but arbitrary state that is given by a density operator and defined by some quasi-probability distribution functions, such as Wigner function, Fushimi function, or Glauber-Sudarshan P function, then we can write the evolution in that form, where again, F capital is some affine transformation of complex plane. So if we want to consider the random evolution where Hamiltonian is random, we also need to average this construction according to some probability measure and consider the expectations of such transformations. So we move on the general task of averaging of random affine transformations of functions domain. We can consider random operator valued functions acting in Rn of this form, where A capital, B capital, H, and J are real random variables, R capital and R small are random smooth functions, and all random variables are assumed to be jointly distributed, so they can be dependent of each other. Also, we assume that some technical conditions are satisfied. I want to pay attention of A5 conditions, that trace of operator A is 0. In case of our setting, where we consider only unitary the dynamics, this property holds automatically. And actually, we will suppose that other properties holds too. So if we have this, and our random affine transformations also define random operator value function on the bounded in the space of bounded operators on L2, defined by this formula, then we can prove the next two lemmas. The first lemma is an estimation for the norm growth for expectation of transformation UF, and the next, and the lemma 2, is the property that the closure of operator of derivative of this expectation is a generator of a C0 semigroup. Having these two lemmas, and applying Chernoff theorem, we can prove this result, that the sequence of Chernoff averages will converge in tau S topology that was defined in the beginning to the semigroup that is defined by solutions of this Cauchy problem with such a generator. And actually, this theorem allows us to construct some efficient algorithm for numerical solutions of Kolmogorov equations of special type. Actually, in general setting, when we want to numerically solve some Kolmogorov equations, we can use some standard deterministic numerical scheme, but this method suffers from curse of dimensionality and can be applied in high dimensional settings. So usually when we solve the high dimensional problem, we must use some Monte Carlo approximations method for solving such equations. The standard approach is to use Monte Carlo methods, which produce statistical estimates by Feynman-Katz formula, and combined with some numerical approximations by, for example, Euler-Maruyama method for solving the stochastic differential equation. On the other hand, with application of theorem from the previous slide, we can construct numerical algorithm using the Feynman-Chernoff iterations, where we suppose that SI is an appropriate, independent, and identically distributed random operator value functions. And both these methods on the left-hand side and on the right-hand side is mesh-free. But if we assume that SI is an affine transformations, then the method by Feynman-Chernoff iterations have a lower complexity than the standard one. And also for certain norms, it have lower estimator mean squared error. We measure the accuracy of our methods by mean squared error because Monte Carlo methods actually is a statistical estimation. And also this method preserves the smoothness of the initial condition, in contrast to the standard Feynman-Katz formula, where the Monte Carlo estimations suffers from uncorrelated spatial noise. So returning to the random Hamiltonian dynamics, we can consider the Hamiltonian of such form defined up to random vector of parameters and consider iterations of these time evolution operators. Then applying the theorem, the theorem 1 defined before, we can conclude that with some additional assumptions, the Chernoff averages will converge to a strongly continuous contraction semigroup U in the topology of tau S that is defined by this Cauchy problem. And in this case, the transformations F capital also be a fine transformation of complex plane, so we can use our effective numerical method in these cases. Also, in some problems, it becomes necessary to take into account also an accumulated common phase factor. For example, in problems when we model not the whole system, quantum system, but only the part. And in these problems, this common phase factor becomes relative phase factor. And we need to model it too. Actually, this phase factor is evolution of this phase factor is also an affine mapping, so we can incorporate it in our naturally incorporate it in our algorithm. On this slide, there is a described setting for evolution of some quantum system. I won't really want to go deep in the details, but actually in this setting, the observable P actually measures this phase factor between two quantum states. And we can model the evolution of this observable by our algorithm. There is some plots. The first left plot is the left plot corresponds to the unitary evolution without decoherence or without noise. The second one is a time evolution of some random dynamics. Actually, this is just one realization and of this dynamic. And the third one is a Chernoff average of this dynamics, which model a non-unitary evolution of quantum system. And also in this task, we can not only model evolution of some observables, but we also can model evolution of density operator by using its by using evolution of quasi-distribution of this density operator. And here is plots for error estimates for our method. Here we have that the different columns correspond to different norms for estimate errors. In first row is root of mean square error, and as we use statistical estimations, we can decompose it to a bias term and a variance term. And the second row is a bias term of error, and the third row is a variance term of the error. Blue line correspond to our Monte Carlo Feynman Chernoff algorithm, and the orange lines correspond to Monte Carlo Feynman-Katz standard Monte Carlo with Feynman-Katz formula. And we can see that in most often case when we use L2 norm, two methods are very similar, and errors are actually the same. But for our setting, when we use affine transformations, method of Feynman-Chernoff iterations are more have lower complexity, so it's faster than the standard one. And in the case when we consider errors in other norms like L infinity, C1 or C2, the method of Feynman-Chernoff iterations became more accurate, actually because of lower bias term of the error. And we can see here that in the L2 norm or L1 norm, our method actually have higher variance, but this higher variance is compensated due to lower bias, and the errors are actually the same for these two norms. So in some cases, for some tasks, this method can be more preferable. Method of Feynman-Chernoff iterations can be more preferable than method of Feynman-Katz estimation. And here is the last slide where produced list of some relevant works of other researchers in this field. Actually, I want to point out the work of Ivanov and Alexander Teretenkov, the first one, where authors considered the similar problems and derived an analytical solution for moments evolution. And this is another approach for such tasks where that is convenient when we don't want to produce estimations of density operator, but only interested in evolution of some finite moments of density operator or some observables that can be defined as combinations of some finite moments. And other works in this list that are considered similar tasks. Actually, it can be a lot of works in this list, but I just pick some of them for illustration. So this is all that I wanted to report today, and I will be glad to answer questions if you have some. Thank you.
Thank you very much. Please, questions, comments.
Well, I have a question. Do you know that in Chernoff theorem, estimates of the rate of convergence are known?
Yes. I'm sorry, I interrupt you.
I gave a talk about this, about my joint results with Professor Oleg Galkin on the first OPSO conference 2 years ago. So you can use not the classical Chernoff theorem, but our theorem, and you will get estimate on the rate of convergence. Will it be constant over n or constant over n square, and so on?
Yeah, thank you very much. It's really important questions, and I read your works on this problem, and actually we have some numerical estimates of these error rates in actually this task. We have estimations m square for convergence of in the operator norms. And actually, I think that this is some general results that there is always be about n square for this diffusion equations like this.
In general, it is constant over n. Constant over n square you will obtain if your Chernoff function is good enough.
Yes, yeah. Thank you. Really, the choice of Chernoff functions will increase the rate of convergence in this case.
And what can you say about the working time of the algorithms where you show two variants with graphs? Probably on the next slide. Here, yes. What can you say about working time? Not about the error, but the working time.
Yeah, actually, in this task, this is low-dimensional task, and the working time is within the minutes. But if we scale it to high-dimensional tasks, in this case, the time will be grows linearly with dimension because we use Monte Carlo technique, and this is one of the advances of these methods. But also, the method of Feynman-Chernoff iterations here, which is depicted with orange lines, also has less times of working times because of it uses approximations of operators and doesn't generate random path for each separate point. So it's faster than the standard Monte Carlo Feynman-Katz method. It is pointed on this slide where Monte Carlo for Feynman-Katz formula have O big of n m complexity, but Monte Carlo by Feynman-Chernoff iterations have n plus m complexity, where n is a count of points in output where we doing our estimation, and m is the count of random paths that we consider before averaging.
This is very promising. This is very promising.
Thank you.
There is time for further questions, please.
Sorry, I have a question. Well, it's more a curiosity, perhaps. You know that for Lindblad equations, there is also the numerical simulation with and computation with the Belafkin stochastic Schrödinger equation. Have you compared the two methods?
Yeah, thank you for the questions. Actually, these errors on the last slide is depicted where the target, the true value is estimated by numerical scheme by solving the ring with equation, because we haven't analytical solutions here. And we can use it here because of low dimension. If we consider the high dimensional problem, even if we have a ring with equation well defined, it's hard problem for solve it numerically, because deterministic numerical scheme will have very large complexity in high dimensions. So it can be computed and in low dimensional tasks, but we can't use it in high dimensional. And if you want to approximate the solutions of this ring with equation in high dimensions, we should use some methods like Monte Carlo, and it will be very similar to this approach when we use Monte Carlo method for modeling Fokker-Planck equations for quasi-distributions.
Okay, thank you.
Other questions, comments, remarks, please.
May I give some comment on this report? Thank you, Rustem, for your report. And I only want to note that this method gives us the opportunity to estimate, to obtain some probability estimations. For example, the estimations of type of low large number for the probability of deviation of random composition of random operators from its mean values. And it is also interesting topic which will be studied in the future, I hope.
Yeah, thank you, Всеволод Жанович.
Thank you. Well, if no other questions, then let us thank the speaker. Thank you very much.
Thank you.
And I think I announced the